Excellent job, Hadley. As we all, those of us who have been around San Diego for a while, this is Tijuana and San Diego, very highly populated, important metropolitan area, and local cooperation and coordination between stakeholders on, either side of the border on a local level. We're in a time where large-scale political currents affect a lot of things, right? But what's going on here is we share natural resources with a large city on the other side of the border, and there's a huge chasm in GDP per capita and in adaptive capacity and in ability to tolerate higher energy prices and all of these things that are leading to this terrible condition at our border. And remember, the lowest income people in San Diego living in this area. And I just personally, editorial statement, I think we owe our planet and our communities better than to allow an artificial construct like a border, not only to be politicized in the context of immigration, but all of that politics to inadvertently or negligently be weaponized against human health is disgusting. So sorry for the editorial, but this Tijuana River issue. I hope it gets fixed one day, but this, I think there's a moral imperative that's bigger than just San Diego, that's maybe bigger than just the United States, but US and California and Mexico to get this issue addressed. I really think that there shouldn't be political controversy about that. It should just be, we have a shared important resource and we should protect it together. And the kind of trajectory where this is headed, if we don't get serious about this, where does this lead? So great job, Hadley. And our next presentation, we have a person up here who's had to learn a lot in terms of adjusting and adapting in life, and that's true for everybody. And some of the things that I don't do too well sometimes I get really passionate about stuff, and my passion gets out in front of my objectivity sometimes. Sometimes I can be a bit normative and have strong feelings, and I've learned to, law school and all this stuff, to be more dispassionate and analytical, and by doing that, I see instead of just seeing what I want to see or what is like laser focused, you actually see the kind of the world more as it is, and then just this maturity has brought me objectivity, right? And that has made me able to learn more quickly. And I just think that the characteristic I've noticed from Jan from the beginning is just this capacity to learn and be objective and see reality for what it is. So to actually take in the correct boundary conditions, Jan would be a pretty okay large language model, I guess. But the point being, in all honesty, that ability to approach a problem and see the facts objectively and analyze the facts objectively and apply logic and reason and not let your own biases and normative filters and everything distort problems, that's a huge triumph in learning for people. And that just comes across as like a default mode for Jan. And I was able to see that because a lot of very, very similar interests, and he would read something and have a take on it, and then I would be like, oh, that makes a lot more sense. So I'm grateful to have somebody that I really learned a lot from this year, and also the context of his capstone I learned while advising. So Jan, thank you for the learning opportunity. Scaling American Sustainable Aviation Fuel, an investigation into effective policy. Jan Chiquier, floor is yours.
Okay. Thank you, Corey. I'll try to meet those expectations. Hi, everyone. My name is Jan Chiquier, and today I will be diving into the aviation sector, specifically looking at effective U.S. domestic policy strategy for scaling American Sustainable Aviation Fuel, or SAF. I'll be saying that acronym a lot, so that's what it stands for. So a quick overview of my outline. I'll be talking about the motivation for focusing on the aviation sector, an overview of the different SAF, sustainable aviation fuel, production pathways and their domestic potentials, an overview of LCA methodologies, life cycle analysis. How do we actually quantify the emissions that we're reducing by using SAF instead of conventional kerosene? And then talking about the targets that the US has outlined based on projected demand and how can we meet those with effective policies to scale domestic production based on the different pathways, and then a lot of thank yous. So what is the motivation for focusing on aviation? Well, aviation demand is sky high. We consume 100 billion gallons of jet fuel each year, and that amount is only expected to grow to 150 billion gallons by 2050. If we put this in the context of emissions, this currently accounts for 2.5% of our global energy emissions, and again, by 2050, some sources say this may grow up to as high as 22% if the sector's emissions are left unchecked while other sectors decarbonize. So unfortunately, aviation is really hard to decarbonize. It's what's known as a hard-to-abate sector, but it doesn't mean that its emissions can't be neutralized. But before we get into that, let's say for a second we did try to really decarbonize aviation, which means no carbon coming out of the tailpipe of the plane. What would be our options? Well, we could try hydrogen, but the problem with hydrogen is that it has a much lower energy density, specifically much lower volumetric energy density. You would need 4 times as much hydrogen as conventional jet fuel to get the same amount of energy. This means larger fuel tanks, heavier planes, more drag, and the green hydrogen itself today is struggling. The same is true for electric aircraft. Again, batteries are much less energy dense, in fact, 50 times less energy dense, and you would basically need really, really heavy batteries mounted onto planes, and you don't need to be an engineer to realize that the plane's not going to go really far. So some people say, okay, we can't decarbonize. Can we keep our fossil fuels and simply offset them with carbon offsets? When you buy a plane ticket, you'll often be offered this option. And if you do choose to buy the carbon offset, I commend the good intention, but unfortunately, the majority of them are scams in that they're really hard to verify. And for a sector that's projected to have as many emissions as aviation, it's not a sustainable long-term strategy. So what can we do? The name of the game for aviation is not to decarbonize, but to not use fossil fuels either. It's to defossilize aviation by getting our liquid hydrocarbon fuels from other sources. And that's where SAF comes in. SAF, Sustainable Aviation Fuel. So the way SAF works, it has a cyclical carbon impact. It either uses carbon sources that were going to go into the atmosphere anyway, such as used cooking oil, which if you put in the landfill will become methane, or its very production process sequesters carbon, such as crops that are grown to make biofuel. What's great about SAF is that it predominantly is a drop-in fuel. It can be used directly with existing aircraft and fueling infrastructure, so we don't need to build new planes or new pipelines, which avoids emissions in and of itself. It is slightly different from conventional jet fuel in a chemical property called aromatics, which has to do with the way it interacts with the fuel tank is it basically prevents the tank from swelling and leaking, which would be a safety issue. So because of that, a SAF can only be blended up to a fraction of 50% with standard jet fuel, although higher fractions are being worked on, but nonetheless, it still offers emissions reductions. So what kinds of SAF are possible? Today, there are 4 primary pathways, and each can be made with a variety of feedstocks. I'll be going over these 4 main ones. There's also some additional ones being experimented with. But despite all these pathways, the SAF industry is actually really nascent today. It currently accounts for only 0.3% of all jet fuel. In 2024, this meant 340 million gallons. Now, the Department of Energy projects that by 2050, our domestic demand is going to be 35 billion gallons. Notice the difference between billion domestically and million globally today. And they have set out this Sustainable Aviation Fuel Grand Challenge where the goal is to produce all of that with SAF by 2050. So we have a long way to go. And importantly, it's important that we don't just only find the right pathways that are truly scalable in terms of domestic feedstock potential and cost, we have to make sure that we're actually making SAF, truly sustainable aviation fuel. And that's actually, I found, very difficult to assess. So going over the first pathway, I'll give a quick overview. HEFA, hydrotreated esters and fatty acids. It's currently the dominant pathway in the US today, or in the world today. The first commercial SAF plant in the world was opened nearby here in Paramount, California, and uses HEFA. The feedstock here is FOG, fats, oil, and grease. And basically, I'll keep the chemistry at a high level here. The oils are deoxygenated and then undergo cracking and isomerization to make jet fuel. The main benefit of HEFA, and the reason why it's so dominant today, is that among the different SAFs, it is the cheapest option. So like I mentioned, the feedstocks are fats, oil, and grease. The cleanest way to make it is by using residual fats, oil, and grease, and that gives it a very low life cycle analysis rating of 13.9 grams of CO2 per megajoule. For reference, conventional jet fuel is at 89. The only problem with HEFA, despite being cheap, relatively cheap and clean, is that it has a very negligible scale. There's only so much used cooking oil in the world. We can't power all our planes off of it. So it has been a very good proof of concept for kicking off the SAF industry, but it's not scalable. There is talk of intentionally growing plant-based oils to increase production, but even under the most generous estimates, that would only increase capacity by a couple billion. And when you intentionally cultivate plant-based oils, you lose a lot of that sustainability. It's still cleaner than jet fuel, but it's significantly less clean because you're tilling new land. The next option, gasification, which uses the Fischer-Tropsch process, which has been around for a while using fossil fuels. Its feedstock is also biomass-based. It either uses residual agricultural or forestry waste or municipal solid waste if it's biogenic. The problem here, and basically what happens is you put that waste under high pressure and heat to create a synthetic gas, and you turn that syngas into SAF by synthesizing it with carbon monoxide and hydrogen. The problem here, though, is that it's extremely expensive. But on the other hand, the ICCT, the International Council on Clean Transportation, does project that domestically it does have a high feedstock potential, and its LCA is also very clean relative to conventional jet fuel. So before I get into the third kind of biofuel, which is alcohol to jet, which is the trickiest one, I want to quickly just talk about eSAFs. eSAFs, or electrofuels, are a very exciting pathway that are not yet approved by the ASTM. And ASTM stands for, although it stands for American Society for Testing Materials, this is the international standard for jet fuel safety. The way eSAFs work is that they use ideally renewable power to produce green hydrogen from water-based electrolysis and obtain a CO2 source primarily from direct air capture. You can also use biogenic sources, but primarily it uses direct air capture, and you synthesize your hydrogen and your CO2 together to produce this liquid hydrocarbon. So in theory, it can be very clean. It'll be as clean as the power we use to power it. And the feedstock potential, because you just need water and air, are in theory virtually unlimited. It's a new technology, not yet approved, and its cost is really high right now, and there's very low activity in the US. But in Europe, there's a tremendous amount of startups that I'll get into a little bit more later. And this is why it's really one of the primary pathways, because of its high feedstock potential and ability to be scaled cleanly. So the third biofuel, alcohol to jet. In my opinion, the trickiest one to really analyze. It's moderately expensive, less than Fischer-Tropsch, but more than HEFA. Essentially, here you use different feedstocks such as corn, sugarcane, or switchgrass that undergo fermentation to produce alcohol. That alcohol then undergoes a series of chemical reactions to then be upgraded into SAF. From a domestic perspective, this really means corn ethanol. 94% of all US ethanol is sourced from corn. This is about 14 billion gallons in 2022. At a 59% yield rate, this could produce between 7 and 8 billion gallons of SAF. ICCT projects 6.89 billion gallons. But that is assuming that all of that ethanol were to be allocated towards SAF production. Right now, the vast majority of ethanol is used for blending with gasoline per the renewable fuel standard. But there is a strong chance that a lot of that supply would be freed up given the electrification trends of road vehicles. So it's moderately expensive. It has high feedstock potential if we can divert enough of it towards SAF. But the real tricky part of alcohol-to-jet is its sustainability. Today, there are two main LCA methodologies out there, CORSIA and GREET. CORSIA is, again, LCA's life cycle analysis. CORSIA is both an emissions trading system and it has its own LCA methodology. It was established by the Aviation Agency of the United Nations. And GREET is more of a standalone computational model. Now, they primarily differ in a sub-factor of emissions called ILUC, or indirect land use change. This is a relatively newly studied field. As you can see here on this graph, which shows their emissions ratings for the corn ethanol to jet pathway, they actually more or less agree on the direct supply chain emissions, but they disagree on ILUCs significantly. And this really applies mostly to the alcohol to jet pathway because that's where you're intentionally cultivating crops and displacing land to produce your fuels. Indirect land use change is basically the idea that if you convert agricultural land that was previously used for food to grow biofuels, you're going to have to grow that food somewhere else and use up more land. So this doesn't apply as much to HEFA and gasification because they mostly use residual fuels, residual biomass. But for alcohol to jet, it's a big deal. And so as part of my capstone, I tried to read as much as I could on it to determine, okay, to what extent is it really clean? And in addition to finding that the literature was very conflicting, I found that the different SAF conferences that I attended were also very contradicting. It was really hard to get a straight answer from people. An executive from GEVO straight up called indirect land use change a fallacy, as you can see here, which I thought was really interesting. But then I also spoke to what I believed were very objective experts, Dr. Benavides at Argonne National Lab, which actually works on the GREET model. And here at UCSD, we have Dr. Richard Carson, who's also known as the most cited environmental economist in the world. They both said that they don't know, which is fine. But it's important to, approach this pathway with that knowledge that we're not really sure right now, and we shouldn't necessarily full send it until we really know. So an overview of the different pathways and how they do in terms of capacity, sustainability, and cost. Now let's bring up that domestic Grand SAF challenge from the DOE. 35 billion gallons. Again, HEFA very limited in feedstock potential at only about 1 billion gallons. So in terms of a policy framework, it's not really going to get us in the long term. It's great for today. But looking at that 35 billion gallons, we have to look at the 3 other pathways. Gasification, Fischer-Tropsch, is mostly hindered by high costs. It's going to follow the same life cycle as any other innovation. And truly only time will tell if the R&D that's been invested into it will bring down costs. I mostly focused on alcohol to jet and eSAFs because I believe they are trickier pathways. Alcohol to jet due to its questionable sustainability, and eSAFs because if you do the math here, biofuels at best can give us 15 to 20 billion gallons. If we really want to meet meet our 35 billion gallon target, eSAFs are going to have to produce over 15 billion gallons by 2050, and we're currently at 0. So we're critically behind. So in terms of addressing these 2 pathways, I think that for the alcohol jet pathway, we need to launch a renewed independent effort on corn ethanol to determine its LCA, now factoring in ILUC, indirect land use change. This is a question that has been looked at over the years by various groups and institutions, but ILUC is relatively recent, and it's what CORSIA and GREET are arguing about. I think that the JASON group could be an interesting group to independently answer this question. Moreover, based on the results of that study, only then can we really know what direction we should take. Should we accelerate road vehicle electrification through EV incentives and charging infrastructure subsidies to free up more of that ethanol supply? Or are we going to realize, okay, this really is not sustainable in the long term and we should incentivize producers to switch to other crops that have not been established but could potentially be cleaner? The renewable fuel standard also has this problematic grandfather clause where it basically exempts producers of clean fuels, including ethanol, that were established before 2007 from having to meet the standard greenhouse gas reduction criteria in order to generate credits. If we find that ethanol will be a significant SAF feedstock in the US, we shouldn't reward dirty production. So I would recommend that we remove this grandfather clause. And then in terms of American eSAF, we are critically behind. Again, we would need about over 15 billion gallons to meet our targets. Europe has already figured out that the eSAFs will play a significant part of the SAF future. In fact, they have, in addition to a mandate for all SAF, they've established a sub-mandate for eSAFs at 1.2% of all total jet fuel uplifted in the European Union by the next 5 years. So they're taking aggressive steps on this because they know it's going to be an important solution. This also places the US right now at a risk of a future competitive disadvantage if we don't tailor some legislation specific to this pathway. Some options to do so would be to give eSAFs additional incentives in the current SAF 45Z tax credit, prioritize it for grants under the SAF Grant Challenge's Fuel Aviation Sustainable Transition Program. And also, right now, the 45V green hydrogen tax credit is under threat from Trump's big, beautiful bill, HR 1. I think we should spare the credit because green hydrogen will be important for eSAF, and it could potentially finally provide the offtake demand that the green hydrogen industry has been needing to scale. And this can not only help scale eSAFs, but could also allow the $8 billion Hydrogen Hubs program to maybe finally see a return. And with that, I would like to thank my committee, Dr. Corey Gabriel. Thank you for being a sounding board for my ideas. Dr. Jacobson, thank you for your insights on emissions trading standards, fleet electrification. Gary Grimes from World Energy, thank you for your insights into the SAF industry. And then a few more professors, Richard Carson, Paula Benavides from Argonne, Gordon McGord, and Claire Levesque, thank you for your insights on the green hydrogen industry and for helping me get organized, Julia Brown, and Jada. Thank you. Cassie.
So if you don't know the answer to either of my questions, please don't feel obligated to answer it, because coming from a pilot perspective, I just am curious about some things. So do the use of any of these fuels require like a change in the way that the engine is built or any additional like add-ons to the plane itself? And then I was just curious if the use of any of these fuels affects just flying performance, engine performance, and stuff like that, if you happen to know.
Yeah, no, great question. If they are blended with the adequate amount of conventional jet fuel, then no modifications to engines need to be made. If we do pursue 100% SAF options or neat SAF, then it's possible some fuel engines would have to be modified. In terms of flight performance, there is no reported deficits. Okay.